Hello students, today let us start our session with stereochemical aspects of SN reactions from the chapter HALOALKANES and HALOARENES. What do you mean by stereochemistry? Stereochemistry is dealing about the spatial arrangements of groups or atoms about the central carbon. So in this case we are going to discuss about the nucleophilic substitution reactions. How do they change their position of or the spatial arrangement of groups attached to the carbon. So before to know about the nucleophilic substitution reaction related to stereochemistry, we have to learn about some fundamental concepts of stereochemistry. What is called plane polarized light? A plane polarized light can be generated by passing monochromatic light through a nickel prism. Monochromatic light, usually they travel in all the possible directions. They can propagate in all the possible directions. But when the monochromatic light is passed through nickel prism, then the propagation of light is condensed to a single plane. Such light is said to be plane polarized light. Solution of certain compounds are capable of rotating plane polarized light either in clockwise direction or in anti-clockwise direction, and such compounds are called optically active compounds, and the phenomena is known as optical isomerism. So the compounds which are rotating the plane polarized light to the clockwise direction are called dextroisomers or D-isomer or plus isomer, and the compound which is rotating the light in the anti-clockwise direction are said to be minus isomer, levo-isomer or L-isomer. This D and L letter should be in small letters, and these D and L that can also be replaced by R and S, the uppercase of R and S. R for rectus and S for sinister. Rectus means right side, like dextro right side, and sinister or levo, that is the left side. So the dextro, it is meant for the right side rotation or clockwise rotation of plane polarized light, and at the same time the levo is representing the rotation of light to the left side, and the direction can also be given as plus and minus isomer. So what kind of compounds are capable of rotating plane polarized light? We said in general they are optical isomerism, and the compounds are optically active compound. When do the compound can be optically active? To be an optically active compound, it has to satisfy certain condition. One is asymmetry, the other one is chirality, and the third one is non-superimposability. What is called asymmetry? See, some compounds are capable of changing their spatial arrangements of the groups in three-dimensional pattern. So when they are changing their groups, the spatial arrangement of groups, they are capable of rotating the plane polarized light to the right side or the left side based on the spatial arrangement of groups. So in this case, the molecule should have an asymmetric condition. First of all, Louis Pasteur, he only observed that certain crystal compounds are existing in their mirror images. So the formation of mirror images of certain crystals only laid the foundation for stereochemistry. Further on, it was taken by Wantoff and C. Liebel in detailed manner, where they studied about the concept of stereochemistry independently, and they just took about the tetravalency of carbon atom. They just considered about the tetravalency of carbon atom. The carbon, it has 4 valency. If all the 4 valencies are satisfied by 4 different groups, then the carbon, it is said to be asymmetric carbon, because it loses its plane of symmetry, or it is also known as stereocenter. So the about which only the 4 different groups will be changing their spatial arrangement. So such compound having that asymmetric carbon is termed as chirality, or the carbon is known as a chiral carbon. So carbon with the 4 different valency that can be represented with an asterisk symbol. So it specifies that the carbon is asymmetric carbon and it is a chiral carbon because its 4 different valencies are satisfied by 4 different groups. So the property of the molecule is said to be chirality. So this is chiral. The next property is this chiral molecule, when it is reflected by a mirror, it can produce the image. The image and the object should not superimpose each other. That property is said to be non-superimposability. So when we take a carbon with 4 different valency A, B, C and D, the valency of the carbon is totally 4 different groups. When it is placed in front of the mirror, we can get its image. So that image will be A, C, D and B. So in this we may find the head and tail of the molecule remains same, but the left and right of the molecule just changed its position because of its image. Now this image, when it is placed over the molecule, we may find the D is on B and the B is on D. Such condition is said to be non-superimposability. The molecule with the chirality should have the other property of non-superimposability. That is, the molecule and its image do not superimpose each other. And this property also satisfies about, we can find the arrangement of the groups B and D exactly changed in its mirror image. If the molecule, it rotates plane polarized light to the clockwise direction, it is said to be plus. But the image, that will rotate the plane polarized light to the anti-clockwise direction. So this makes anti-clockwise direction and here it makes a clockwise rotation. So because of the differing in rotation of plane polarized light, it gives rise to the 2 isomer, plus isomer and the minus isomer. Plus can also be called dextro, or it is to be represented as D isomer, dextro, and this is as levo isomer. And these isomers are said to be enantiomer. So enantiomers are the isomer of optically active compound which do differ in their rotation of plane polarized light, but their physical and chemical properties remain same. Then what do you mean by racemization? Racemization is nothing but when these 2 isomer, that means the plus and minus isomer, when it is mixed together, they may lose the property of rotating the plane polarized light and the molecule and the mixture becomes optically inactive. Let us take an example how the molecule and its mirror image become non-superimposable and whether the given molecule is optically active or optically inactive. So let's have the 2 propanol. 2 of the valency same, and the other 2 valencies are hydrogen and OH. So by seeing or looking the molecule itself, we can find it has no chiral carbon or asymmetric carbon. Anyhow, let us proceed for its explanation. So to this molecule, when I place the mirror, I can get the image of this molecule over here. So it seems the image and the molecule are non-superimposable because when I take this molecule and keep over here, the OH goes to left side and the other goes to right side. So it seems these 2 molecules are non-superimposable. But when this mirror image is rotating about an angle of 180 degree, so the molecule which are lying above goes to the down one and the molecule which are lying below will go to above the plane. So when we do that 180 degree rotation, you can find this is the wedge shape and this is the dashed one. Wedge shape is observing, we are observing the molecule, and the dashed line just behind the observing molecule. So when I rotate this molecule to 180 degree, then the molecule of the behind the one goes to observer and the other one goes to behind the molecule of observing one. Now you may find the structure 3 with the structure 1. It looks alike. When this molecule is placed over the first one, they are exactly superimposed one another. So the mirror image it seems non-superimposable, but after 180 degree also the molecule which is resulting do not superimpose with its molecule. That is called non-superimposability. Let us find one more example, 2-butanol. 2-butanol, CH3, CHOH, CH2, CH3. So I can write CH3, CHOH, CH2, CH3. It has 4 carbon atom. One of the group is methyl group, other group hydroxyl OH group, and the third group hydrogen, and the fourth group is ethyl group. So this carbon is asymmetric carbon. Now let us take that asymmetric carbon with 4 different valency. This methyl group just behind the plane and this ethyl group just above the plane. Now when a mirror is placed over here, I am getting that image of this one, in which we may find they are once again non-superimposable. But after the rotation of 180 degree, the molecule which is just above the plane, it goes to below the one, and the molecule which is below the plane, that goes to above the one. So we can find this CH3 just behind the plane, it is now at above the plane, and the ethyl group that is above the plane, that goes to behind the plane. So that makes now the structure 3 that can be placed over 1. We may find the ethyl over methyl and methyl over ethyl. It seems the molecules and the image are non-superimposable, and hence 2-butanol is an optically active compound. Some more examples of the molecules or the compounds having chirality. We have 3-chlorobutane, lactic acid and tartaric acid. So this molecule, they can have either one or more chiral carbon. See, in 3-chlorobutane, it has one methyl, ethyl, chlorine and hydrogen. So 4 different valency, and hence the carbon is chiral. But CH3 or C2H5, they have similar hydrogen atoms, so they do not make a part of chirality. Next, the lactic acid. Similarly, the carbon, it has a methyl group, carboxyl group, hydroxyl group and the hydrogen, that makes the chirality. And tartaric acid, it has 2 chiral carbon, one with the CH3HOH, where the complete structure makes one more valency. Similarly, the second carbon has CH3OH, and where this makes the complete part of 4th valency. So these are some more examples of chiral molecules, and most of our carbohydrates have the property of chirality. Let us explain about the mechanism of SN1 and SN2 for optically active alkyl halides. In SN2 reaction, we have already seen the resulting compound will be inverted product, because the nucleophile that attacks the carbon just opposite to that of leaving group, that means the backside attack. So that results in the formation of inverted product. We said that is a inversion of configuration or Walden inversion. So that can be found by taking the optically active compound of -2 bromooctane. So in this, the carbon, it has one methyl group and one hexyl, one hydrogen along with halide ion. So let us represent the molecule in its 3-dimensional. When the nucleophile approaches the carbon, see, it approaches the carbon to the side opposite to that of carbon. So that makes a transition state, in which we discussed about the halogen will be a leaving group. That means it is taking away its shared pair of electron, and OH it has to share its pair of electron to the carbon, and thus it makes the compound. So due to the backside attack, the resulting molecule which is formed from transition state, that makes inverted product. So this is called inversion. So here what I have taken, the compound is minus 2-bromo-octane. That means the compound, its solution is capable of rotating light to the anti-clockwise direction. But the product formed upon the nucleophilic substitution, it gives rise to the dextroisomer. That means this product is capable of rotating light to the clockwise. So the direction of rotation of plane polarized light changed as a result of the reaction. So this confirms SN2 reaction. It alters the spatial arrangements of the group about the central carbon atom, and the resulting product will be inversion. Let us take 2-bromobutane to explain about the SN1 mechanism of optically active compound. So in this case, first step is the slowest step, from which the nucleophile is being removed. As a result of it, we will get the carbocation. So the carbocation, where the hybridization changed sp3 to sp2 and tetrahedral to planar, that is trigonal planar, everything altered. So when the molecule, after the removal of nucleophile, it forms a carbocation. This carbocation is free from the nucleophile, that is the halide ion. So as it is free from the halide ion, the incoming nucleophile that can attack this carbocation on either side of the direction. So let us have this carbocation, in which suppose OH minus just attacks the carbon to the side same as that of halogen, we will get the compound of retention, because we may identify this molecule and this molecule in which the spatial arrangements of the groups are similar. So this molecule, it gives rise to the product which is retaining its groups. That's why it is called retention. And the other way, if the OH group attacks the carbon just opposite to that of halide ion, what will happen? The entire spatial, that is the entire groups of the carbon just altered, and the OH goes to the side opposite to that of halide ion. In this we may find the spatial arrangement of groups totally inverted. So this gives rise to the inversion. So as they are differing in the arrangement of groups in a plane, they can rotate the light one to the right and the other to the left. So the one we have minus butane 2-val, that means this resulting molecule able to rotate the plane polarized light to anti-clockwise direction. At the same time, the inverted product will rotate the light to the clockwise direction. See, from this we can identify what would be the nature of this molecule. This molecule is minus 2-bromobutane. We have to find a beauty of stereochemical aspect of SN reactions. We discussed about SN1 and SN2, where the primary alkyl halides ready to undergo SN2 reaction, tertiary alkyl halides ready to undergo SN1 reaction. Depends on their solvent. And SN2 we said they have to take place in polar aprotic solvent, and SN1 we discussed they have to take place the reaction in polar protic solvent. But when we discuss about the stereochemical aspect of nucleophilic substitution reactions, in which whatever the compounds we are taking for the explanation of SN2 and SN1, they are secondary alkyl halides. So secondary alkyl halides only can have the 4 different valency. That's why we are taking the secondary alkyl halide. So secondary alkyl halide depends on the groups which is attached to the carbon and the nature of the solvent they may decide to follow whether SN1 reaction or the SN2 reaction. Elimination reactions. The last session we discussed about elimination reaction where we found only one beta carbon from which the dehydrohalogenation takes place. Suppose if we have the alkyl halides having more than one beta carbon, then there would be a formation of two different dehydrohalogenated products, but one of which is said to be a major and the other is said to be minor. How it is decided? This is what decided according to Zaitsev's rule. So according to this rule, the major product will be the one in which the doubly bonded carbon atoms should have more alkyl substituents. So whenever we find the alkyl halide of having more than 2 beta carbon, we have to analyze to which direction of the elimination of hydrogen from beta carbon can give rise to the more alkyl substituent for the product. Such a way only we have to decide the elimination. So let us take an example of CH3, CH2, CHBr, CH2, CH3. So one side I have propyl group, the other side I have ethyl group, and the carbon it carries the bromine. So in this is my alpha carbon, this is beta carbon, and this is also beta carbon. So the elimination is possible as a result of this one. So here also we can make eliminate, and here also we can do that eliminate. So in presence of alcoholic potassium hydroxide, the elimination it may lead to such a way. So where I am getting the product of CH3, CH2, CH2, CH double bond CH, CH3 plus the other beta carbon. It has ethyl group and in which I have one more hydrogen, so that can proceed the elimination like this. So what happened? I will get the double bond between CH and CH, so the product will be CH3, CH2, CH double bond CH2, CH3. So by comparing these two products, this doubly bonded carbon, it has one propyl group, the other one is simply methyl group. But in the next case, the doubly bonded carbon, it has ethyl group and that side also ethyl group. So the number of alkyl group to the either side of doubly bonded is similar and more number of carbon, and hence this molecule is said to be a major and this is a minor one. Major minor is nothing but that depends on the yield of the product. One will be in large yield, the other one will be in less yield. Based on the yield only we are classifying them as major and minor. We studied about the preparation of Grignard reagent, that is organometallic halide using alkyl halide and magnesium ribbon in dry ether. And we said the Grignard reagents are highly sensitive and more reactive and stable. Even in presence of water or alcohol or even amine, it gets converted into their hydrocarbon. So because of its highly reactive nature, we can get the derivatives of hydrocarbon. So let us find uses of Grignard reagent. The first one, it is useful for the preparation of the three classes of alcohol: primary, secondary and tertiary alcohol. And these three classes of alcohols are prepared only from the carbonyl compound. So out of carbonyl compound we have aldehyde and ketone. In aldehydes, formaldehyde and acetaldehyde we have. So other than formaldehyde, the rest of the all aldehydes will give secondary alcohol. but formaldehyde alone with the Grignard reagent able to form primary alcohol, but the ketones always give tertiary alcohol. So to obtain the three classes of alcohol, we have to select the corresponding carbonyl compound. Primary, you should get that formaldehyde or methanol, or except primary alcohol, if you want secondary alcohol, you must take any other aldehyde except formaldehyde. Ketone able to form tertiary alcohol. You may find only in this carbonyl compound just we have added a hydrogen and an alkyl group. This is CH2O. See, I have CH2O. This CH3 from the Grignard reagent and this hydrogen due to hydrolysis. So to the carbonyl group, the CO group, we are going to add one alkyl group and one hydrogen to the oxygen, upon which we are getting primary, secondary or tertiary alcohol. So from the knowledge of the product also, you can able to identify what would be the carbonyl compound and what will be the Grignard reagent. Because here I have taken only methyl group. You can have any size of alkyl group over here. Based on that, the product will be formed. So we can select methyl. Instead, you can have even R group. R group represents any saturated alkyl or even unsaturated group you can take. So let us find how the reaction proceeds. In Grignard reagent, as it is a part of metallic halide, the metal should always have a positive charge. So this metallic bromide being magnesium plus 2 valency, so it when it solves Br minus 1 plus 2 minus 1, the rest of the charge for magnesium is 1 and the corresponding negative charge is given to methyl group. So here in Grignard reagent, the alkyl groups are nucleophile. They have a negative charge and electron rich, that's why they are behaving like a nucleophile. And in the case of carbonyl group, that oxygen and carbon is the functional, in which oxygen more electronegative than carbon. So oxygen can withdraw the electron like this, and hence it produces a partially positive charge and the negative charge. So this Grignard reagent, as its alkyl radical and the metallic halide, can be added between the carbon and oxygen. So here addition reaction takes place. Opposite charges we have to add. So MgBr plus, that goes to oxygen, and the alkyl group is minus, so that goes to the carbon plus, that is electrophilic site. So it makes the compound. And the respective compounds on hydrolysis, it yields once again water HOH, and this OMgBr only be the reactive site, so in which it breaks like this. So here you are adding one hydrogen and OH to the MgBr, so the product is formed. So depends on the carbonyl group, we can able to prepare primary alcohol, secondary alcohol or tertiary alcohol. The mechanism of these reactions are quite similar. The next application of Grignard reagent is to prepare the carbonyl compound. Carbonyl compounds are aldehyde and ketone. If you want to prepare aldehyde, then the reagent is ethyl formate. Formic acid and ethanol able to form ethyl formate. So this is ethyl and this is a formic acid group formate. So the name is ethyl formate. So this ethyl formate, when it is treated with methyl magnesium bromide, as usual, it undergoes nucleophilic addition reaction, because CH3 is minus. So the nucleophile adds to carbonyl group and hence the reaction is nucleophilic addition. So this CH3 approaches carbon and the double bond approaches the MgBr. We are getting this adduct. These are said to be adduct. And upon hydrolysis, in presence of acid, this ethoxy group that moves towards the magnesium, so we are getting MgBrOC2H5. Due to the movement of ethoxy group towards the carbon oxygen, the single bond is into a double bond, so we are getting aldehyde. Such a way If you want to prepare ketone, then any acid halide we can take. Acid halides are RCOCl or ARCOX we can take, RCOX, or we can have ARCOX. Any acid halides with Grignard reagent that gives ketones. So here I have taken benzoyl chloride. The name of the compound is benzoyl chloride. When it is treated with methyl magnesium bromide, here once again same nucleophilic addition, same pattern of reaction, nucleophile methyl to carbon and the oxygen to MgBr, we are getting this adduct. This adduct on hydrolysis, once again the halogen, carbon halogen bond breaks and it moves towards carbon oxygen, where chlorine combines with the MgBr, it forms MgBrCl and we are getting ketone. Preparation of carboxylic acid, for which we need to have only carbon dioxide. The structure of carbon dioxide is C double bond O double bond O, to which when we have alkyl magnesium halide, say CH3 MgBr plus carbon dioxide, this gives rise to the nucleophilic addition of CH3 to this carbon and one of the double bond with the metal, so that makes CH3 CO minus MgBr with double bond. So this is upon hydrolysis in presence of acid. We can write the H2O as HOH, where the oxygen it abstracts that proton and OH goes to magnesium bromide. So the product will be CH3COOH plus MgBrOH. So we prepared carboxylic acid from Grignard reagent and simply carbon dioxide. Preparation of ester. Esters can be prepared from ethyl chloroformate. This is ethyl form, this is a chloroformate, so the name is ethyl chloroformate. Let us take methyl magnesium bromide, CH3 MgBr with C2H5O COCl. So here the methyl group to the carbonyl carbon and the MgBr to oxygen. So the product, the adduct will be C2H5O COMgBrCl with CH3. Now during the hydrolysis in presence of acid, the chlorine atom, that CCl bond that migrates towards the MgBr, so C2H5O COCH3 plus MgBrCl. So by this method we can prepare the ester. Ester is RCOO group, so CH3COO. The next one, preparation of cyanides. Cyanides can be prepared by taking cyanogen chloride. Cyanogen chloride formula CnCl. This is called cyanogen chloride. So this also undergoes nucleophilic addition reaction with Grignard reagent CH3 MgBr, and the structure of cyanogen chloride is C triple bond NCl. So here the pi bond of this one that moves towards one of the pi bond and the methyl group goes to the carbon. So the product is CH3 C double bond N MgBr with the Cl. Once again, this is on hydrolysis in presence of acid. We may get the movement of carbon halogen towards the MgBr. So the product is CH3 C triple bond N plus MgBrCl. So here the double bond C double bond N, due to the movement of carbon halogen that makes a carbon triple bond nitrogen. This is called ethane nitrile or methyl cyanide. Preparation of higher ether. To prepare higher ether, we have to take halogen substituted ether. One of the halogen substituted ether we can find CH2Cl, that is, this is chlorodimethyl ether, or we can say chloromethoxymethane. Let us take this compound CH3 MgBr plus CH3O CH2Cl. So in this case the MgBr just adds with halogen, so we will get CMgBrCl plus to the place of the replacement of chlorine is replaced by methyl, so the product is CH3O CH2CH3. So if we have a halogen substituted ether, when it is treated with Grignard reagent, it may give rise to the higher member of ethane. Here I have dimethyl ether, this is it is ethyl methyl ether, so one more carbon is increased, and moreover these Grignard reagents are used to increase the number of carbon atom in the product. So Grignard reagent is used for the step up reactions. These are the usefulness of Grignard reagent. We prepared most of the derivatives of hydrocarbon. Okay students, let us close our today's session and we will start our next session with the next topics and the new informations. Until then, bye bye.